The techniques that I'm presenting are used to various degrees of forensic works that I have.
Doctor, I would like to ask last time it's the same
Yes.
video. It is
Yep.
a translation?
Yeah.
In the Chinese, whatever.
Literal translation. Yep.
It is the translation.
Literal translation. So the way that it reads, which is very bad English, is how the Chinese words are written. And it's it in a way makes fun of people who misuse the language, but at the same time this is one of the most popular direct translation of Chinese words that are used. So that but nonetheless it's a very inspiring thing to do. Yeah. Okay, so we have and this is one of the things very, very important to recognize, is that in forensic work, most of the time you will go to the very traditional way of doing things. Okay, yes, people are trying very hard to develop advanced technologies, but at the same time, we realize that the people in the lower profession does not necessarily understand all the details about the other techniques. Okay, and so realizing that aspect of forensics, it makes it harder for new technology to entry into investigation. Okay, and as I mentioned, the Molly case. The German has developed a numerical simulation for that particular case, but as I mentioned, finite element analysis are not necessarily accepted in the code of law. Okay, so those are very important. But from a forensic investigator's perspective, your job is to use whatever technique that will best describe what happened. Okay, so sometimes computer animations may be used to help your case, okay? But then how can that be applied into court evidence is a tricky question at this point. I think only the judges can decide whether that particular simulation can be applied as a tool, okay? So we have tonight we have many experience of doing traffic counting, tape measurements and all that. So all those so all these are traditional tools that you just have to use. Okay, and this is a picture of what we have done here in India. Yep, yep, and where we 10 kilometers away from you.
So besides that bridge, that is the highway.
Yeah.
So we didn't get load testing.
Mm-hmm.
So that time luckily Professor Chen was there.
Yeah.
Or 2 load testings you are there.
Yes, yeah.
In 2007.
Right.
I was not there. And after that you came in 2013.
Yeah, and then we do more. Yep. Yeah. But this is a very traditional way. Even in the U.S. today, we're still using the same technique for load testing. Okay. You may ask, why do load test? Well, load tests, the intent of the load test is to prove a constructed bridge or an existing bridge still has its design capacity. Okay, and as we discussed in the very first class, how do you know the strength of a material? The only way you know is to load it until you reach that design capacity. Okay, and this shows the dial gauge that was placed on top. So this very traditional method is still very useful, but very, very tricky to do. Okay, as if you have experience using dial gauge, if the dial gauge gets sticky, then you will not move. Okay, and then your numbers become very erroneous, and it puts people at risk. Have to climb up to the scaffold and literally do the measurements. Okay, ruler measurements is good, but it is also something very, very important for you to realize that what is the resolution of this ruler? Well, this is in inches, I think. Yeah. So it will be. So you look at the scale. It has between 6 and 7. For example, there is 20. So 1/20 of an inch, okay, is the resolution. And if you use this ruler to measure displacement, very small displacements, it will not be valid. Okay, so you have to realize that in measurement science, resolution of your instrument becomes extremely important. Okay, and sometimes these are the questions that you may not discuss in court, but as a scientist, as an investigator, you have to know that basic knowledge. Okay. And this is also very important pertaining to our discussion of, so when you write a legal document, okay, if you were to report a measurement of this nature, how many decimals you need to report? Okay, so you cannot report, oh, I use this and I measure, there is a deformation, say for example in this case, 2 feet and 0.00000025 inch. That 0.0025 is beyond the resolution of your measurement. You cannot get that accuracy. Okay, so your measurement is wrong. And whenever you are reporting something that was not accurate, even if the legal people don't understand that, if it comes to a point of argument, then you would discredit you. Okay, so those are very, very important things that you have to keep in mind. Okay, this is Dr. Shen, and we used this set of pictures. It was, I think, in one of the years I came, and then he was have to do a medical checkup. So we went to the NIT doctor, but it's a good representation of what measurement means to a forensic case. Okay, so a person has a problem, and then you use the technique to measure. Okay, you have to use the right technique. It cannot be something arbitrary. Okay, and that has always been an issue, especially with geotechnical investigation. Okay, so one of the arguments that I have involved in was a case in Taiwan. They have a tunnel, and the tunnel has a groundwater problem. So this company proposed to use, the tunnel has some collapse, and it was due to groundwater effect. So this company suggests to use ground penetrating radar to do the inspection. Well, anybody who's in NDT know that ground penetration radar cannot see through water. Okay, so what is that technique applied to? It's totally useless. But but the people, the consulting company doesn't understand that. They just know that, hey, I have this very powerful instrument I want to use, and cost the client a lot of money. So me and my colleague were arguing with them, suggesting that you should use something else.
So what will be the specific application for this GPR?
Ground penetrating radar is good for density measurements for pavements. Yeah, even in the tunnel case, the tunnel lining, if the lining is good or not, if it's sufficient thickness, you can use ground penetrating radar. But whenever there is groundwater in the back, then it changes. Yeah. So and rebar is another application. Yeah, yeah. So those are, and also another very important thing is the depth of penetration of ground penetrating radar. It's very limited.
For the deck slab method.
Oh, absolutely, very good use. Yeah. Yeah, in fact, that technology really become useful for pavements and deck application. Yeah. Okay, so this is the doctors.
Natarajan, this Natarajan.
Yeah, Natarajan and Natarajan. Yeah, Dr. Natarajan and Dr. Natarajan. Okay, vibration is one of the most common problem facing civil structural failures. Okay, especially when we have structural techniques that developed for lighter and lighter structures, okay, lighter and stronger structures, then vibration problem becomes more and more critical, okay. And so these are some of the instruments that we use for vibration testing. This is a shaker, okay. So you can use this kind of shakers for a number of applications. For example, you can shake the bridge at one particular resonant frequency, or you can give a random vibration, and then you can generate many, many modes, okay? And this is what I was discussing, an impact hammer, okay? So an impact hammer, it hits on the ground, it actually generates a broad band of multiple modes, okay? And all the energy is limited by the force that you apply. So it is a very stable method for excitation. However, the processing of the data becomes very complicated, okay? And when you use any of those instruments, especially the traditional instruments, you have to be careful because it usually has a power supply, okay? So those are the gauges here. You have to make sure it always have sufficient energy input into your hammer, okay? So doing this kind of instrumentation, you have to make sure the cables are working, okay? And one of the challenge in doing a full-scale structural testing is the daily temperature variation can influence on your electric cables, okay, and cause noise into your data. So those are extremely important things to be careful. And these are the different contact head to your hammer, okay? And they have different hardness. And as a result, you generate different band size of your testing, okay? And you may not be able to see clearly, but there is a triaxial accelerometer attached to the end of this cable here, the blue cable. And that is what you use to measure response, okay? So that kind of sensors you attach to a structure, you have to make sure you maintain perfect contact, okay? And so there are many times that is the biggest struggle because you'll be a bridge that is, maybe 50 feet high in the air, and you're already very, scary on a scaffold, and then yet you're trying to apply force to make sure the sensors is set up. So there's a lot of tricks in doing this kind of work. And so in the past 20 years or so, we also are investigating using wireless sensor. Okay, so wireless sensor, while it is cool because it's small, you attach, you don't have to carry a lot of stuff with you, especially managing the cables. But wireless sensors, just like your cell phone, the signals can drift. Okay, so you have to be close. So this is the antenna for the sensor, and the antenna has to be looking at your antenna on your base station. Okay, so the line of sight becomes extremely critical. Okay, and those are details in when you go out in the field doing this kind of test. Okay, so this is a specific. And another challenge in forensics is that you may have a set of equipment, and you always have to be mindful that equipment need to be updated. Okay, and so this particular sensor, the manufacturer is already gone. The company is already gone. So we don't have the software. The software was running on the Windows XP. And of course, now we're Windows 10, so the software cannot be used anymore. So now I'm shopping for new sensors. Okay? And, while it's just an investment, right? But then the data that you collected at that time, okay, now you're using a new set of new equipments. Are you going to be able to reproduce the same data? Those are, very high-level issues with condition monitoring, health monitoring, forensics. That is just there. Okay, and one of the things that I have personal issues with people using this kind of sensors for embedded systems for bridges is that this sensor will not last longer than your bridge. Okay, so when people die, some of your neural systems, your sensories, die slower than your brain. Okay, and that is good. Why? Because throughout your useful life, many of your senses are useful throughout. Okay, and that is why the doctors can base on your responses to tell how good you are. But if your sensor lives shorter than you, like, my hand has a problem, but it's already numb from way back, then the doctors cannot tell anything. And this is this kind of micro electronic-based systems. Okay, the microelectronics, just like your cell phone. How many cell phones have you owned till today? Many, exactly. You know, so they are not used to sustain for a long time. Okay, but cell phone has its use. Like the first time when I showed Shen, my cell phone can measure vibration. He was just so excited. He asked his Minu to buy him his daughter to buy him an iPad. And then I told him, sorry, it only works on cell phones and not on iPad. But yes, there are a lot of apps that you can actually measure vibration. And there are free apps that you can download. So this is an example. So you can download these apps, okay, and then you can measure the vibrations on your cell phone. Yeah, any cell phone there is such an app now. Okay, so look up, and it's very, very useful. Okay, way back, I think it was 2002, the University of Sheffield has a group of students that measure the Millennium Bridge in England, the walk bridge, using cell phones. You know, so everybody stand and then measure the vibration using the cell phone. So these are very handy. And in 2014, when we were here, we went to a GB. At that time, I couldn't bring any of my equipment. So we used our cell phone to study the vibration problem at the GB Engineering. They have a crane that moved and then got stuck. So we use that to measure vibration. So there's a lot of handy tools you can do for inspection. Okay, now there are some times you may require to do much more elaborate testing. Okay, and one of the very elaborate testing methods is called modal testing. Okay, this is when you have to distinguish between the different modes, and the only way that you can determine what the different vibration modes represent is to do a full-scale modal testing. Okay, that means you have to construct the shape of the deformation of the structure. Okay, and so we use very large sensors. Those are low-frequency triaxial sensors, and then you have to, and in this case, it's a concrete pole. We have to put the sensors at the right position, which is on the top, and then you have to lay the pole down so that you can simulate free boundary conditions. Okay, so this is a very elaborate. Take months to do this kind of study. Okay, but and you can see this gentleman is using a hammer. So the way that you do this testing is you designate many points and you impact them. Okay, so it involves high-level skill. Okay, and then you can construct literally for different frequency the shape of the deformation of the structure. Okay, so when you take structure dynamics or vibration engineering, you learn about those, but you don't physically see them until you build a valid finite element model, or you do this kind of full-scale model testing to validate. Okay, so for some building vibration problems like foundation vibration on the structure, you know, you wanted to know where is the problem, and the only way that you can tell that is to do, for example, this slab has vibration problem. How do you know whether it's a boundary connection problem or if the slab doesn't have strong enough stiffness? Okay, or maybe somewhere you have a weak poor concrete sections. You have to do a full-scale model testing of this facility. Okay.
In this interpretation,
yeah.
Is the model testing result is the more reliable or the finite element result is more reliable?
Oh,
see the curve,
yeah.
It is almost same.
Yeah.
But all finite element results cannot be same, no problem.
No.
Cannot be.
Yeah. So we have two techniques. One is called model updating. So you have your actual experimental results, and then you update your finite element model so that you can get the right material property. Okay. But the other is, if you just have a finite element model and then you have the actual testing, because you're not certain about the boundary conditions. So you need both. Yeah, you need a finite element to show you, oh, this is what kind of boundary, and that's why you have this frequency. And then you do the testing and then match the frequency. Yeah, so a lot of times we have to build both finite element model and the experimental
Do you have any other
model.
alternate methods to validate?
Yes, yeah. So if it's a simple structure such as a beam or a column, you can use theoretical solutions, like using a beam with different boundary conditions to validate. That's the third answer. Yeah.
We can bring
Right. Yeah. Yeah. Yeah.
other structures. It is
Much more complicated.
very
Yeah.
complicated.
Yeah. Yeah. This is an area that when they make requests, this got to be a big project, like a bridge failure or that kind of problem. Otherwise, it's not cost effective enough to conduct such study. This is a similar technique that we use to monitor blasting. Okay, so in this case, the client is very concerned that this pole structure, there are 3 pole structures, steel and concrete and wood, and they are concerned that the mine blasting would damage the structures. So we have to do the before and after monitoring of the structure to make sure that it doesn't damage or the boundary conditions change. Okay, we also use the same technique for tunnel studies. So a lot of times tunnel has a lot of defects. Okay, and those defects, even though they are static problems, but they can change the structure stiffness and mass significantly. Okay, so when we do full-scale model testing, we can actually determine the different modes, and then use the different modes to determine where is the weak or damaged zone on the tunnel. Okay, so these are more infrastructure-related kind of problem, but you never know, when you go do a consulting work, whether it's going to be bridge or building or something. And this is why, our argument that if you're a forensic engineer, it really doesn't matter what type of problem you're facing. Okay, so even though I don't have, I never designed a tunnel. As an investigator, I can go and do investigation. I can find where the problem is. Okay, I have enough knowledge, geotechnical knowledge, for me to perform such work. Okay, and this is where is a sticky point when you argue with lawyers. Okay, because they want to discredit you. Okay, you're not a tunnel designer. You may not even through so many tunnels in your lifetime. How can you be a tunnel engineer? Well, I have very strong geotechnical background, okay, even strong geology background, okay. And then 2 is I'm doing this in using a scientific investigation technique that not many people have the qualification for, okay. And this is how you establish your qualification. And at the end of the day, again, it's your investigation. How do you lay out your argument that prove to the judge, this is what happened. This is why I say it happened. That's important, okay. And so this is where. But if you, and I will show a case where you are not even an engineer, okay. How do you even present a qualification? But with that said, there are times that the lawyers can get people who are not engineers, like technicians, who has been doing that work for many, many years. And he has gained enough experience, we call this grandfathered, qualification, that he can go, because engineering license is not a very long period, okay? And so many, many people who are living today in their 80s, during their practice, they never have licensing experience, okay? And I imagine when India has a full license for the whole country, at that time, many of those older engineers will use grandfathered experience as a qualification for this kind of work. Okay, so yes, qualification is extremely important. But again, the argument should be that have you done a thorough investigation? Okay, because that is the value of your work. Okay, it's not necessarily your qualification. Okay. This is, we use similar technique to do like an impact echo kind of test. So this is a cylinder, concrete cylinder cast with steel casings, okay? And this is not for any particular case application, but you can see we were able to tell the results of a poor concrete and a good concrete case. Okay, well, the poor concrete they already load test. That's why the concrete already cracked. So using this technique, we were able to tell the difference between the wave propagation in the cylinder. Huh? Yeah. Yeah. Uh-huh. Yeah. Oh, no. Yeah, very good question. So the reason he's sitting there is because this is the easiest way to do the testing, right? But he's not doing vibration. He's doing a wave propagation. Yes, yeah. So okay.
I think he's checking whether the concrete has any internal void.
Yes, yeah, internal problem, yeah. Yeah. So when you do impact testing, you are exciting the whole structure, right? But when you look at when you impact, okay, so this is input. Okay, when you impact onto the structure, you will receive a response. Okay, and the time difference between the two arrival is wave traveling. Okay, but this carries a lot of the characteristics of the vibration of the system. And you're right. If we were to take this and then convert to going through Fourier transform, you will get a lot of those modes. And those are vibration modes. Okay? And so we use the time of arrival to do the wave propagation, and then use the response to do the vibration. Yes, yeah. Time delay is the way. You can actually also relate the time delay to wave propagation, but it's a little more complicated. Okay, but one technique you can actually get two results. Okay, yeah. So that's another advantage of doing an impact-based vibration testing. Oh, yeah. Good to meet you, man. Yeah. Yeah, so this is not a conventional application, but we do that as a demonstration in class, that you can use ultrasound wave. This is almost like an ultrasound, but low frequency wave. Yeah. So using the time of arrival. Yeah. And this is the data collection. Again, this company is gone. So at that time I'm really looking for because I changed job. And the new school doesn't have that much resources, so I'm looking for all kinds of low-cost system. And this one particular IoTech, I really like the system because at that time Texas Instrument has a very expensive $60,000 data collection system. But this one company manufactured this very small device. The Texas Instrument was like a car. You have to push around. And they come up with this really light stuff, very useful for us. So I've been using that for a number of years. But now the company is also gone. So this is a big challenge for us. And then this is a shaker test. Okay, so this is a military bridge that we are doing a shaking test. Okay, and so when you do this kind of testing, and in fact a lot of civil bridges, you can use the same technique. Okay. So you put it on the ground, and the ground act as a reaction. Okay, so the shaker is strong boundary, so the stinger can push the bridge. Okay, and the stinger, it acts as a control. So we use plastic stingers because if you put too much force, you will crash your shaker, right? But the plastic will buckle. So that way that you prevent damage to your system. And then you can see we put an accelerometer next to it. Okay, and you can see how many cables that we have used. So underneath this bridge, we put I think 18 sensors. Because you have to construct a full 3D model. And this is where laser scanning becomes very, very useful because you get so many points. The technique is what Navani was describing as using the Doppler effect, laser. Okay. So this is so to simulate free boundary condition, we use this kind of rubber tires to support the structure. Okay. So that is another very important aspect. When you do, everybody structural engineer should understand this. Okay. When you do finite element modeling, okay, you have to know the boundary condition. But when you do forensic investigation in the field, you can actually change the boundary condition to make sure that boundary condition fits your theoretical, or trying to make it as close to your finite element model as possible. Okay, and so you can so for example, if I were to test this slab, if we were on the higher on the top, I wanted to make sure that I have fixed boundaries. I can put heavy sandbags around, so make sure that the boundaries has strong rigidity when you do the testing. Okay, provided your goal is to find damage in the middle and not the connection. So those are tricks that you just learn when you are doing work in the field. And over the years, we're also trying to develop our own device to measure vibration. Okay, so this is a handheld device that we are hoping for study of bridge cable vibration. So cable stay bridges, the cables, like Tacoma Bridge, So what caused the Tacoma Bridge failure? The latest study is that those hanging cables damaged. Okay, so this is the another famous bridge. This is the Delaware Bridge. Okay, so you can see we did a demonstration of our device, and we invited many state DOT engineers to come and show them. Okay, and in this case, the Delaware Bridge hangers have excessive vibration problem due to the boundary conditions. Okay, and so that was the drive for developing this device. So we're envisioning this device. We can, just handheld. It's very light. You can go to inspect every hangers. And you can just go across the bridge testing. Okay, and so that's our motivation for developing our own device. And then we also measure the vibrations. Okay, so using the device, this go into a little bit tricky part of the business. Okay, so at that time, this device you have to develop the algorithm. Okay, how many modes do you actually need in order to get, because again, you go thinking about automate the process. So you have to make sure that you always get the same band of frequencies. The goal is to see how the frequencies change, right? So you need to know, what is this 14.62 hertz? Is that a first mode bending, second mode bending? You need to know, okay, on the string. And so we did this bridge to validate. And in this case, I think there are 16 cables on both sides. Okay, and so this shows, and actually every cable is 4 of them. Okay, four 7-stranded cables. And so we use a laser vibrometer to test every one of those cables. And the result is that we can validate and actually show how each of the cables. The goal of the device is actually back calculate what is the tension level on the cables. Okay, so based on the right frequency, you can back calculate using very simple T equal to square root, frequency equal to square root tension over 2 pi function to calculate the back calculated tension. Okay, and then I'm going to show again on the LiDAR technology, but show a little bit different perspectives. Okay, so these are most of the things that Navneet has discussed yesterday. Okay, oh, go too fast. Okay, so LiDAR system. Yesterday he showed an animation that the laser actually scans this way and this way, right? The effect is that you actually create a half hemisphere, okay? And the ground, of course, you also scanned, but then what you will not be able to see is right underneath the laser, Okay, so depends on the height of your laser. You have actually creating a circle on the ground. Okay, this is our first generation laser, much heavier and bulky, but you can imagine this whole thing will rotate this way, and then the optics inside rotates this way, and the laser itself rotates this way. Okay, and that's how it generates. And then the system has a power supply, which is a very big lithium-ion battery. That battery cost me $5,000, and it got damaged. And we called the manufacturer, and they say we no longer supply or support this kind of. So I bring it to a battery specialist, and when we open up that battery, I was shocked. Okay, inside it has many tiny AA batteries taped together. Yeah, and then there is a microchip on top that measures the voltage of each of this. No, the lesson here is this is the same kind of battery in the electric car, in Tesla. So the lesson learned from a technology perspective is this thing cost me $5,000 when all the batteries combined cost less, way less. You know, if you run your car that your life is depending on a bunch of these tiny little batteries, lithium technology is going away, if I have the right to say. Because that is not what we envision technology. You know, they literally use duct tapes, you know, paper tapes to tie them together. And how long can the paper tape last? You know, and so this is one of the issue, again, me against the microelectronic based system. Okay, it doesn't have that sustainability. How many of you know what BlackBerry is? Not BlackBerry, Raspberry Pi. Okay, yeah. So some of you know what Raspberry Pi. Raspberry Pi is a small device that you can basically teach students, train them to write basic programs. And you can use it for many attachments on different sensors. Now people are suggesting to use Raspberry Pi for monitoring our infrastructure. You know, that thing, we break 2 or 3 a year, you know, in the lab because they are made of plastics. You know, so your sensor has long last living than your structure. Otherwise, the sensor is not contributing anything to the system. It's very important, okay? But we as especially electric profession, okay, for many years we have moved away from heavy power engineering, okay? Everybody's going to the micro and the computer technology. So we literally miss a whole generation of people who are able to handle heavy powers, okay? And so 10 years ago, when our College of Engineering started the Power Infrastructure Center, we realized that there's nobody that can teach power engineering class, power electronics. Okay, so we have to hire from other school. And this is a problem, you know, especially when I present the lecture on disaster, okay, that was targeted towards the electric power. Of course, you know, ties back to civil infrastructure because we are equally important. You know, the towers are built by us, the nuclear power plants are built by us, okay? Electrical engineers are dealing with the product. We're dealing with the infrastructure, okay? So how can we ensure in this climate scenario that the power system is survivable is the research challenge today, okay? Anyways.
The red light that is blinking on.
Oh, that's just to show the system is working. Yeah, on, yeah.
So these rays are harmful?
No, they are eye safe. Yeah, they are class 2 eye safe. Yeah, so that means you can look at the laser for 2-3 seconds and no problem. So when they go very fast. Huh? Class 1, yeah. Mm-hmm. Yeah, the wavelength is, yeah. Yeah, you actually cannot see in this case because they didn't dye the color, so there's no laser beam like this one. This one is dyed red, okay, but this ones are blank. Yeah. Okay, we have used, again, it's just a technology, but how do you apply it to forensics? It's up to your imagination. So Navani already described measuring clearance for bridges, okay, defect measurements and so forth, deflection. So all these are but the most important thing is the archive function, okay. So you have an electronic data that you collect, okay. But just before I leave, the client, our manufacturer come and did a demonstration which disturbed me a lot. So what happened is the advancement of the software control, like Cloud Compare, has advanced a lot. So he literally showed me a point cloud of a parking deck, and there's a car there, and he can take that car and then move it to another spot as if the car was parked at a different spot. Now that is scary, right? Because can you imagine you do a 3D point cloud data and then another party take your data and then they start doing some modification? Yeah, it's kind of like you have a Word document, right? You share the Word document and then people go in there and change the language. So there need to be a PDF kind of point cloud, okay, that people cannot manipulate. That can be permanently timestamped for your investigation at this day, this time, and this moment, okay? But those are, still in this profession that is still being debated and struggled, okay? Forensic applications, LiDAR application in forensics doesn't, probably only 15 years, maybe even less, okay? So now it's an accepted practice in forensics, but in the legal court, but still people are not fully understand this yet. Okay, so going back to the thing that we showed you yesterday, so this big area we are trying to study the retaining wall movement. Okay, so today I'm going to elaborate a little bit on what we have done. Okay, so this is the oh no, actually no. When I talk geotech, then I'll elaborate. But this is the structure. Okay, and this is our full scan. Okay, because it's 3D, you can turn and manipulate. And when we construct this, we use a lot of sphere on the ground. Okay, so that the sphere is the one that ties all the scans together. But you can see, as you move away, the old laser scanners, your point scatter, your resolution, spatial resolution, you can visibly see it gets worse and worse as you go further. Okay, so this is something that you have to keep in mind. And all these are trees. Okay, so those are noise. Okay, and then this is what we've seen yesterday. Our application. This is fly ash. So we are studying how rain hits on fly ash and then, rush off. Okay, so this in coal mines and in energy. In coal-fire plant, they usually store those fly ash on site. So they have ash ponding. Okay, and then as rain washes, this ash run into water, then contaminate your water. Okay, so that's why we do this study. So we use laser to investigate if we can quantify how much is this scouring of the ash from rain. Okay, so this was actually work done in China. So we send a student to China and build out such a facility so that you can simulate a single line of rain and then see how much wash off it gets, and then use a laser scan to quantify. Okay, and these are the targets that we use. And this is the laser system, Chinese built. Okay, and as I mentioned, this strong light has big impact on electronics. Okay, so it broke my camera and not a sustainable technology. And this is the system. And this also is my first international experience. Okay, so I have never done work in China. This is the first project that we do. And then I realized that it's very difficult to do business with Chinese. I am Chinese, but I'm not from China. So, it's very difficult. And this is actually their dean. So this is the gentleman technician. He kind of act like he owns the equipment, but we all know equipment owned by the university, right? But he was very, stuck up. He didn't want to loan this to this Chinese guy who doesn't speak proper Chinese, And so the dean actually come in and oh, here's the cigarette. Please help this poor guy from America. So so he loaned us the equipment to do the testing. Yeah, the dean actually have to physically help me negotiate the equipment. Anyway, okay, so this, as I described, I think it was yesterday, I showed a little bit. One of the challenge in engineering mechanics is really from a theoretical mechanics perspective, we kind of separate stress and strain. The reason is because we are so focused on how the structure is damaged because of strength, okay, the stress reaching exceeding the strength, okay. We didn't realize that actually studying the surface deformation is also very important, okay. But in theoretical mechanics, that two components are not combined, okay. So if you present the whole physical deformation of a system, okay, how do you translate that to the actual stressing in the system? Even using finite element is difficult. That is why some of the finite element programs, you want to show stress, it shows stress. You show deformation, deformation. But you cannot show both stress and deformation simultaneously. Okay, and that is a big problem. So trying to address that issue, we did a very small experiment in the lab. Okay, and luckily from measurement science, I think there is a way to converge the two. It's just how to do it. I'm not understanding that part yet. Okay. But we basically use a piezoelectric sensor system that can create a guided wave technique, okay, on that plate. And then at the same time, we measure the external surface deformation using LiDAR. Okay, so this plate, we clamp it on the corner, okay, and then we put this piezoelectric sensors. So what those piezoelectric is, it generates a acoustic high frequency, so like ultrasound wave, okay? But then this is a system developed by Stanford University. So each one of this is a receiver and a transmitter, okay? And so when you start this system, you can imagine many waves going through. So if you have a crack going through, that system will be able to detect where the crack is propagating. Many lines going through this, okay? And so this is our technician doing a saw cut. So we do the experiment by slowly cutting progressively and then scan. So we have a lot of data by just going through that, okay? And this is the piezoelectric sensor. So piezoelectric technology is a ceramic patch, okay? When the ceramic patch has a function, the electricity is, when you introduce electricity, the ceramic patch will vibrate. But if you reverse the process, if you vibrate the ceramic, it will generate electricity. Okay, so it behaves as a receiver because if you have a wave coming in and vibrate the thing, it will generate a response. But if you generate electricity through and force it to vibrate, that vibration can go to another one, and that will be a receiver. So it's a very powerful technology, especially for metals. Okay. And then after the test, we force the plate to have plastic deformation. Okay, aluminum plate. And so as a result, you can see that the waves traveling, these are artificial. We just demonstrate. And then you get this kind of result. You literally see as the crack, the saw cut going through, the red zone slowly going down. Okay, the plate. And then at the point where we start making plastic deformation, you see the stress concentration actually go away from the plastic zone. Okay, because the forcing on the two ends, the large deformation, the bending, okay, will result in the stress. So what that tells me is all this stress is relative, okay. And then we use laser scan. So this is laser scan results. So if you overlay laser scan results with the ultrasound or piezoelectric signals, then now you can pinpoint exactly where the problem is. Because otherwise, all of this are relative. Okay.
Can we use this again, Professor?
Yeah.
So we have used this for one element.
Yeah.
Can we use this for another element?
Yes. Yeah. You can detach it and then reapply. Yeah. But the sensors are not very expensive. So yeah. And this is a good system for using like airplanes. So in fact, a lot of airplane has this permanent attached to the wings, yeah, or fuselage. Excitation is the wave, vibration. That's a good question. I believe it's a band of frequencies. Yeah, because the piezo size is very specific. The vibration of the plate, but the difference is you can actually excite different modes of vibration, and that's how you create different frequencies, wave. Yeah, you can decide, or you can automate. So one sensor would excite, and then the second sensor, third sensor, you can actually generate that algorithm. Yeah. Yeah, it's a very powerful technique. There is a group in America trying to use this on concrete. But, so you imagine this tiny little patch, put it on concrete, how much you can excite and how much the energy attenuate.
Goes in the breaking part, I think that will be challenging.
Yes, yeah.
We cannot measure that. Even we face it with the strain gauge.
Right, yeah. Yeah, so I imagine, I've never tried on concrete, but I imagine data will not be very good. Yeah.
It's not good.
No, yeah. Okay, so this is another system that we are developing in our lab. So slope stability is always a problem, okay, when the slope fails, okay. But how can you tell which point the slope is actually starting? So right now the technique of monitoring slope failure is drill a big hole and then put a piezoelectric to measure groundwater level. Dandelion is this wings. Dandelion is the thing that flows, right? That wind blows the flower. Well, so we got the inspiration from the dandelion. So what is, yeah, what we do here is we have a pipe that drill into the ground, yeah, and then we put many sensors, and then we have this stiff wings, and if the vibration, if the movement coming from one side, the wing would change. And then the sensor would detect, this is the direction of the movement.
You don't know how it will.
Exactly. You don't know, right.
So if it hits in anything, it sends and it will give you
the direction of the signal. Yep. And that's what we're developing. Yeah. And so now, just like using the laser versus surveying equipment, now you're looking at the whole area rather than just one point. Yeah, and I'm talking to a sensor manufacturer, so we're trying to make this a wireless system, okay? Because you cannot go on to the slope and then measure, and then the slope carry you down, right? So it had to be wireless. Yeah. And these are some of the tests that Natalie did in the lab. So we developed different stiff wing, and so the stiffness of the wing becomes critical. Right, because the soft wing and how do you determine the stiffness? So we do different tests using stiff and the soft wings. Yeah. Because if it's too soft, then the wing blows and then you artificial noise. So you have to have the right stiffness design. Okay. This is another technique. So this is more. I'm slowly moving into the geotech domain. Okay. So geophysics is one of my background, okay? And geophysics is the method of generating a vibration into the ground. Same thing like model testing, okay? But you use pick up the signals and then trying to determine what is underneath the ground, okay? And this is the typical testing methods. So usually this surface wave testing method, you generate vibration by using a hammer or a drop weight, okay? And then that vibration will travel, and then you have multiple sensors on the ground to listen to the, and then based on the travel wave speed, same principle there, okay? So if you have if you have multiple sensors, okay, so you generate a wave, and then the time travel to the second sensor, and then one that is further away, and then that is one that is even further away. You have a time difference, right? So based on the time difference, you can translate to what is the soil stiffness, K1, K2, K3, K4, through depth. Okay, so now you literally create a profile of the stiffness into the soil. And we use this method a lot, especially where I'm coming from, to study sinkhole. Okay, so sometimes you have limestone that eroded by groundwater, okay, especially in Florida and the coastal area. And that will eventually eat so much of the rock, the surface would sink, okay, and then the house would disappear, okay. And so using this method, you will be able to tell, you know, if this K3 has suddenly dropped, so the way the signal will have a change in wave speed, okay. So that's the principle of this technique. So this is so in our lab we create different weights because you want to go deeper. You have to use a lot more energy. So this is a 50-pound, 20-kilometer concrete block that we built, and then we just take it and drop, and we have up to maybe 50 kilometers. So my students at that time are mostly bigger than me because they can carry those heavy weights. Yeah, but that's me trying to do the same thing. Yeah. This is the sensor on the ground. Okay, so when you do this kind of studies, it's not exposed, but this sensor actually has a needle underneath. Okay. Spike. So the reason is because ground is soft. Okay, if you just put it on the surface, when you do vibration, the sensor is separate, bounce, then the signal will be useless. So it has to be closely in contact. Okay, so any sensor, the important thing is the contact. Okay, that's why we go into remote sensing, because you don't worry about the contact. But using this kind of traditional sensor, you have to make sure they have full contact. And this is an Olsen instrument device. So I'm training students how to collect data using that device. And the geophysics is much more rudimentary because soil is very complicated. Okay, so usually we base on very simplistic guidelines like, you know, very soft soil. What does that even mean? Okay, but there's based on different wave speeds that you can translate into the effects. Okay, and this is where this kind of techniques are important, but the interpretation of the results heavily depend on your expertise. Okay, and so we have done this for many different applications, soil characterizations to evaluate deep and shallow foundations, sinkholes, as I mentioned, which closely tie into abandoned mine. Okay, so abandoned coal mines underground, many times they will result in the surface subsidence. Okay, so if you're in an area where the coal mine is tying with limestone, how do you know, is it limestone problem or the coal mine settling problem? Okay, and this is one of the cases that I have done a lot of investigation. Okay, but just to show you the effect. So this is on the cliff, and somebody's building a deck, and they wanted to know right behind the foundation, what is how shallow is the rock? Okay, so so this is a scenario, and we did the SSW testing, so we can determine what is the thickness of the rock. So the rock, where we did the testing, actually is pretty deep. So you can see the translation. So usually horizontal distance is depth. So the rock behind is actually 10 feet deep, which was really surprised, because if you see here, the rock seems like very close to the surface. Okay, so what's happening is actually, and this is just my theory, okay, is that this lake is actually man-made, okay, and so originally this is hilly mountains, okay, so suddenly somebody make a lake, and then this part of the thing was blasted out, okay, so it seems like you're looking from here, the soil is very shallow, but the actual rock is like this, okay, so you actually have more deposit of soil further away from the cliff than at the cliff. Okay, so many times you have to depend on your understanding of geology to help interpret those data. Okay, this is a sinkhole study case, and this is a very unique case because literally below is a hole. Okay, so many times when we describe sinkhole, it's not really a hole, it's just the rocks start to crumble and fill up the hole. So it's loose rock rather than empty void, okay? And so, but in this case, it literally is an empty hole, a cavern underneath. And so we see a sudden drop of stiff velocity. If you read it as stiffness, we suddenly see this very sharp change of curve. And I argue with my students, this doesn't look normal, okay? But he told me that based on how I teach him to interpret the result, this is what it looks like. Well, when we go to the site, we realize that this church has been dumping rock because the hole already formed, and then he keep dumping rock and then everything that he can find into there. So it actually formed an arch above the hole. And so when we do the geophysics testing, indeed there was a big hole underneath the ground. Okay, and so they have to do a lot of work, very expensive project to correct. Yeah. And then we use the same technique for parking deck testing, okay? And so you can do this for many different applications. And in this case, the parking deck, we actually found the shallow rock at 7.5 feet. Now, here's a very important thing. You notice that how coarse the data points are. Okay, so the resolution of this particular test is actually not very good, and for many reasons. One is the ground is much harder to excite. Okay, and so you have to realize that you don't always get good resolution. Okay, and this is the same result that we present in a different way to show you. We do two tests, and the data are pretty consistent. Okay. Next, I'm going to go into an area that I was involved for the past since 2000. Well, actually, so this is where your career take you in a different path. So when I was in Alabama, I did a lot of wind damage investigation. Okay, and then hurricane starts to hit, and we have several disaster hurricane cases. Okay, so suddenly I found myself jump into disaster assessment for hurricane or cyclone cases. Okay, and in this scenario, it's a little bit different from typical forensics in the sense that you literally go into an area where people die. Okay, and there are many debris and stuff. So it's not your common single structural failure case forensic investigation. So when we go there, you have to be able to be improvised. Okay, so there's no electricity, so how can you carry heavy equipment? So we have to develop our own technique. Okay, and this comes in 20, but this area of study is advancing quickly. Okay, as I mentioned, forensic is a big money business today. Okay, disaster management. It's a big money business. So when we were in the Philippines, I suddenly realized United Nations has world's top military scale cars, because you have to imagine you're going to an island that no electricity is available because the cyclone take out all the power supplies. Okay, so they bring cars, that terrain cars like the SUV, that actually has its own electricity, has satellite telephone, and then very high powered signal transmitters all built into the car. Okay, and you can imagine how much money United Nations take from America to equip. Those cars are even better than some of our military equipment. Okay, but anyways, at that time we start investigating using GPS camera. Okay, and timing is just perfect, because in 2013 there is still no available low-cost GPS camera. Okay, but 2014 when we start investigating, the price of those GPS cameras suddenly dropped. Okay, and so there was a debate: should we buy GPS that has a camera, or should we buy a camera with GPS? Okay, so this is two competing technology, and at that time, GPS with camera cost $25,000, and this is only about $200. So we go with this, hoping that the technology will work. Okay, because we don't have experience, but you can see on the ground. So all these are the GPS position of where we took the picture. Okay, and they are pretty accurate. There are some that drifted, because not enough satellite, and we have some pictures that was like in the ocean, which is not possible. But the error is still reasonable, and we were able to develop several techniques using this. Okay, so you can see the scattering of all this. Why? Because we have 10 people on the ground, everybody with one of those cameras. Okay, so people are roaming around because we have to investigate 10, 20 buildings at the same in a day. So it's very busy. You have to drive, through debris, go to one building, another building, and in a very foreign environment. And everybody just focus on taking pictures of crack and stuff. So how can you go back and then analyze more than 20,000 images? Which building, which picture belong to which building? So we found that the GPS technology really come in handy. Okay, because we were able to relate the pictures to the building. Okay. And it's the same time that we also start investigating how to do capturing three-dimension information of a structure. Okay, so this is one of the experiments we did when I spent my sabbatical here in Trichy, and we were able to look at the architecture sign, which is in 3D, and then I walk around and take many pictures. You can see how many pictures I actually took, and then use a software to tie them together. Okay, and so this is the outcome. You can see that little dog suddenly disappeared. So this is the technology now you can use for drone, okay? And so now more and more drone flight investigations can be done for disaster area.
So the photo that you take with the camera, the GPS coordinates get geotagged with the photo automatically when you take
That's what the difference between GPS camera and regular camera. Yeah. Oh, in fact, I always do this when I do this kind of presentation. So my camera, where's my camera? And just to show you how how careful I am. I actually carry 2 cameras with me now, because this one is very old. Okay, I bought this in 2014, and then last year when we were doing inspections in Puerto Rico after Maria, so I bought another one. So I always carry 2, just in case this one dies. But I will come and take a picture of you guys. Oh, wait, dang. So this is the problem. The older technology, the batteries doesn't last. Did you notice that all the problem eventually is electrical? Who's that? Oh. Okay. Anyway, this camera will work. So I'm able to take a picture of the class, and when I go back, I can show my students what I have been doing here in Trichy. Okay. I remember in 2014 when I was here, and then I have to go to China for a week to teach another class. So when I was travel to China, every stop, Singapore, I would take some pictures, and then when I come back, I can string them together. So, oh, this is where I'm going. What amazes me is when I was in China, I had to take the high-speed train. Okay, and it actually worked. Go to the next one. Oh, what happened? Oh, okay. Okay, thank you. Oh. Yeah. So we're here, okay. So this video I was not able to find. Yeah. Oh, yeah. See. Oh, it actually works. Doesn't it? Okay. Anyway, this is in Philippines. So we literally take many of those buildings and in 3D. Yeah. Yeah. But you can see how badly damaged the structure is. And the fortunate thing is now that I can look at a lot of pictures and then relate to this building because I have this 3D movie of that building. Okay, so no. This is in Philippines. Yeah. Mm-hmm. Yeah, and we also have Vizag. Huh? Yes, yeah, we'll be looking at that. Yeah. And this shows you the principle of this technique. At that time, this again, PhotoSyn is no longer available. I think Google or maybe Microsoft took this out anymore. Yeah, but now there are open source programs that you can do similar algorithm. Yeah. Another technique that we have developed at that time is again because we are not high tech is not available, so we developed this yellow tape method. So we actually bought, this is a yellow tape that we use for fishing in America. So when you caught a fish, we put this on the boat so you can measure how big the fish is, okay, the length, size of the fish. So we brought this yellow tape to the Philippines, and then we put it on the wall so that we can have a reference. Because all the buildings, you don't know how they are designed. You don't know the height of the ceiling. But if you have this, you can use that as a reference to measure. So in this case, you see how many we have put. You can tell the dimension of the structure, and then you can quantify what is the damage. Okay, and then coming back to Trichy, we actually trying to see if we can come up with a theoretical correlation. So we that's the pole at the administrative building, and then we walk. Locusts walk away from the pole and then take pictures, and then use the same picture and then use MATLAB to develop this equation. So now, anytime you take a picture, you know the size of this. You can use that to extrapolate any dimension that you want. Okay, so these are the the very low tech technique that we're developing, but those are very low cost yellow tapes that you can apply to any disaster case you investigate. Okay, and of course this is in the Philippines. So this is we call the rock work analysis. We want to know how strong is the wave pushing. Okay, and so in the Philippines they actually bring rocks from inside the ocean. And so if you know the dimension of this rock and how far away from the wave or the beach line, then you can back calculate the force, because the bigger rock will travel slower, right? And then the smaller rock will travel faster. So we actually did this test, and of course, if I have a laser, this will do a lot of work, but we use the traditional pole to measure. Okay, so in the disaster scenario, you have a lot of unknowns, okay? And you have to go back and do a lot of analysis to determine different effects. And so in this case, we're actually combining GPS, aerial, and rulers. Okay, so when this is Andrew Kennedy from Notre Dame, and he's one of my team members. So when we were measuring the rock size, we took a picture of him, so we know which rock we were at. And then this picture of high resolution of the rock work actually was provided by the Japanese. Okay, so the Japanese was the first to take aerials of the area. So this is very high resolution aerial. And then we were able to combine his measurements, approximate what the rock size, and then do correlation. Okay, so it's challenging. Okay, and next is another technique that is specialized. So I actually have a patent on this technique. Is to use small airplanes. Again, this is pre-drone days. Okay, and then we use high-speed cameras or regular cameras, and then we were able to take aerial images. Okay, and you can do a lot of monitoring. So in this case, for example, we can monitor project development. And the value of what we do is we actually use GPS camera. So every picture you take on the airplane actually are geo-referenced. And then we take that picture and then put it in ArcGIS. GIS, we actually can measure damage. Okay, so the value of our technique here are twofold. One is we utilize GIS analysis software. Another one is my pilots are skilled so that they can take high-resolution images. Imagine at 1,000 feet, your pictures can see cracks on the ground. At that time, there's no such technology. Yeah, and so that's why we get our patent. In fact, right after we got our patent, my pilot got called to Afghanistan for military applications. So the CIA got interested in our technology. In fact, it's the first time I realized that people actually can use the act of freedom to get anything from me. So we got people from government call me and say, okay, there are people require your data, so they request our information from me. I'm like, wow, what are we doing here? Anyways, when we develop this technique, there are a lot of good applications. But just to show you the difference, most of the aerial images are flown using what we call the large format aerial photography. Okay, the pictures that you see in Google Earth and all that are developed by this. This is a technique that they fly at 5,000 feet and then use very big cameras so they can cover a big area. But the resolution of this kind of images are maybe 1 inch, 2.5 centimeter resolution. And using our own technique, we actually use very low cost camera, GPS camera, and then we cut a hole in the belly of our airplane and then mount the camera there. And then all the technique is the pilot. Okay, so we teach the pilots how they fly. Okay, so this is the regular airplane. So this entire technology probably only costs $200,000 US. And a used airplane in the US is about $200,000. Okay, but if you were to contract, oh, it's not going back. Okay, this technique would cost you millions of dollars to do. Okay, sometimes works, sometimes doesn't. Okay, yeah, I will use this meanwhile. But the trick is how you fly the airplane. Okay, and so again, and then when the airplane dips into what we call the waypoint, and then the pilot would start, so always fly with two people. The other guy would just fire off the camera. So the camera takes a lot of pictures. And as a result, we get really high resolution. And we develop in-house software that we can actually map out the crack on top of a bridge deck. Okay, so this is really, really high-tech stuff. And then this is what we call the proof of pudding. Okay, the test of pudding. To prove that our product is good, you have to be able to measure this crack, and next year this crack, what happened to this crack. So in 2 years, in 2 years we were able to use this technique to show. So this is a crack that we took a year ago, and then the next year when we fly, you see the crack changed. Okay. When a lot of DOT engineers saw this, they're just amazed, because that is almost like telling somebody, hey, go to Google Earth, you can see what happened to your building the year after and the year after the year after. Okay, so but at that time, we were able to see multiple cracks change. Yeah, there's a joint of a bridge deck, and then you can see that joint is damaged more and more. Yeah. And we actually fly all over the country to teach aerial photographers how to do this technique. So this is another business model, trying to promote your technology so that more people can participate. And at this time, we are doing this for the Department of Transportation. Okay, so in the U.S. and China has the world's largest bridge network, highway bridge network. So each of us has 600,000 bridges. And 600,000 bridges over a very big continent. Okay, how can you inspect them? So even now, our federal law requires that every bridge needs to be inspected every other year. Okay, but the best we can do is still go to the bridge and look at the bridge. Okay, so this is the reality of bridge inspection everywhere in the world. And so with this technique, we hope that we train enough aerial photographers so we can fly all 600,000 bridges in 1 year. The higher frequency you do the inspection, the easier you can catch when there's a problem. And this is my pilot who went to Afghanistan. Yeah, so he went the same time Bin Laden was caught. So we asked him. He said, "No, this is military secret. We can tell." But
he must be in that operation.
Yeah, we don't know. He's a goofy guy, so I don't think they can trust him. But yeah, anyway, another really, really cool technology is, so we have those pictures, and those pictures are GIS, georeferenced, when they embed into a PDF program. Okay, so now this is a very important part. When you submit a report to your client, okay, a written document, and they have more questions, what do? They have to come back to you, because it's all either paper or a Word document, right? But with this technique, you can actually, if they have ArcGIS, they can open the PDF and do measurements on your pictures in the PDF document. Okay, so in other words, if you don't believe our analysis, you can do your own analysis and prove that we were right. So all these embedded pictures, the engineer can use PDF to literally open up, change the viewpoint, and then go and do any measurements of a particular crack that they're interested. So this is a really, really important part of technology. But this was way before beam was, even exist. Okay, so I'm imagining more of this will even come into picture. It makes our life very difficult because when I was a student, AutoCAD was like version 1.0, I don't know, but it advanced so much. We have the constant learning, and learning. So, anyway, the last slide I wanted to show is fiber optic technique. So there are certain applications that you really, really have to use some technique that can give you more precise. So this particular application here, you see those cylinders. So we are studying how concrete pipes crack. Okay, concrete pipe cracking is random, right? But if you have those fiber optic sensors, you tie around and those fiber optics are strain gauges. Okay, so they are the same fiber optic for all your wire communication, but using high technology, they can cut great lines on the surface. And then when the light travels through those lines, they can tell by the change of wavelength, when the thing was being stretched or not. So it becomes a strain gauge. Okay, and so on these cylinders, we put a lot of those strain gauge on this, and then when the concrete starts cracking, we can actually pinpoint where that happens, because this becomes a continuous measurement method. Okay, so you can tell where and you can tell when that crack happened. Okay, and this are very useful for certain applications, such as pipe, which is underground, you can't see. Okay, so this technique are not new. A lot of bridges in America have already been installed with fiber optic strain measurement systems. Okay, so those data can be used for post-analysis to see what happened to the structure. Okay, any questions? So I think this is the discussion part on the all the technology that I can present. Some of them are a little beyond high tech, but I'm hoping that the lesson learned here is technology is really something that will help forensic investigation. Okay, but at the same time, you really need to realize that. And the value of this series of discussion is really forensic is a business, is a practice, is an engineering practice. Okay, so into this practice, you have to watch out for many, many things, such as the aging of your technology, especially you do a lot of instrumentation. So constantly updating yourself, constantly improving, develop new damage detection methods and so forth are all very important part of your profession. Any questions? Yes.
So in SLS testing,
Mm-hmm.
we were finding that
Yeah.
So with that, we are defining the density as well as the homogeneity of the material.
Right.
So all the data you have got, you have shown there, all the detection has been done on the surface. Right?
On the surface only. Yeah.
So can it be done below the water?
Okay, so you have to understand, I mean, if you have a surface, you can apply it any way you want, right? But dome wheel sensing has always been challenging, okay, because it's hard for you to get a precise location of your sensor, okay? And so, yes, you can do the same kind of analysis by putting the sensors into the depth and then do the same analysis.
So it can affect the sensor.
Effect?
Affect the sensor. If it will be done below the water, then it can affect the sensor, right?
Oh, wait. What question are you asking?
I'm saying that suppose that sensor will be accurate below the water.
Oh.
Then it will
Okay. That is a difficult thing to answer. Okay. The reason is because if I understand what you are saying is, can I do this test, for example, in the lake? Yes, it can be. Okay. But then you have to modify your sensor to accustom the buoyancy of the water as well as the sensor. So whether it's saturated or unsaturated, the sensor will not be able to tell the difference. Okay, so if you were to test this testing, you have to make sure, again, coupling of the sensor and the medium. If you can find a way to make sure the sensor stay within the water, you can do underwater ground analysis as well. Yeah.
Yesterday we discussed about this aspect, sir, about the underwater, certain limitations are there for that.
Yeah,
equipment.
for LiDAR, yes,
LiDAR.
for LiDAR. Yeah, but he's talking about the surface wave technique. Yeah. Yeah.
So earlier you had told that it is very difficult to determine the cracks within the nuclear concrete.
Cracks within
Nuclear concrete.
nuclear concrete, yes. Yeah.
So with that sensor testing, we can do that testing in that section, right?
Yes.
In the nuclear concrete.
For nuclear concrete, yes. However, yeah, NDT, yeah, yeah. You using the surface wave method on concrete surface, right? Yes. Theoretically, yes. However, okay, so the nuclear concrete problem are actually much more refined than that technique. So I mentioned that the technique has low resolution. So for geological applications, it's good because we're looking at several feet of soil or rock change, okay? But when you deal with nuclear concrete, you may have a 3 feet thick wall, but you're looking for a problem that is maybe micro crack or separation of debonding between steel and the concrete. Those are much lower resolution. So using that technique, I don't envision you can find meaningful problem, but theoretically, yes, it can be done. Yeah.
One critical question is
Mm.
there's always been a conflict between traditional results
Testing,
and
uh-huh.
technology.
Yeah.
Like it's always said that the technology, the traditional method is more accurate, and
Yeah.
now technology.
Mhm.
And technology, let's say down the line,
Mm.
if you're using an instrument for a year or a 2 or 3,
Mm-hmm.
it also has its wear and tear. So
Yeah.
there's a compromise
Mhm.
in the accuracy.
Right.
So have you ever faced any difficulty in trying to convince a client that with the technology you get very accurate results?
Yeah, so,
How do you
yeah.
how do you tackle that?
right. So the first question is, as a professional, you always have to make sure you use the best equipment. Okay, so if your equipment is old, you don't use it. If you don't even trust your own data, don't use it. Okay, so you should always make sure that when you go out, your equipment is good and your results is reliable. Okay, so that's, first of all, you are the gatekeeper. You make sure that you don't give people bad data. Most of the problems, the actual issue that I face is the explaining the results to the client. Because some of those analyses are even harder for traditional engineers to understand. How can you even talk to somebody who's not an engineer? Okay, so using this technique, I can guarantee you get good results, but explaining the results to your client, making sure that they are convincing, take a lot of your efforts to convey that. Yeah. But yes, most of the cases I present here, this is the only technique you can present. There's no other means, okay? For example, in the coal mines, unless you drill holes, there's no way you can tell. So you have to use NDT because it's not an option for you to drill a hole. Yeah. So that's the thing. Yeah, but professionally, you should make sure that every time you do the investigation at that time, your equipment is in mint condition.
Because when you see from the Indian scenario point,
Uh-huh.
the reason why I think the technology is not coming into place is
Mm.
because they don't find it very convincing.
Yeah. Mm-hmm.
So still they catch on to the traditional methods.
Right,
and,
yeah.
then-
And unfortunately, this is where our job is to train the new engineers to get used to the new technology. We have to teach them to understand. So, in my institution, I teach NDT, sometimes teach health monitoring, so I can give them the background on signal processing or some instrumentation basics. Yeah, you have to teach them, otherwise new technology will never come in. Yeah, I mean this is our job, really. To change the culture and change the the acceptance of new technology is professor's job. Yeah. Any other question? Yes. Yeah, you have to speak up.
The light source.
Good question. So, because the fiber optic sensor you can apply in any way you want. So if you are interested in crack that is maybe in the radio direction, yeah, then you have to apply the sensor in a different direction. Yep. And it's just like strain gauge. If you remember from your stress analysis class, in order to tell the crack directions, you have to apply 3 strain gauge. So you can do the same thing with fiber optic strain gauge. You apply them in 3 directions so that you know the angle, you know X and Y, and then maybe even Z direction.
Okay, sir.
But again, using this technique, the coupling becomes really important. So I send my students to China to learn how to apply the strain gauge because fiber optics are very fine, okay, and the strain gauge are almost in the micro level. So you have to apply them in a very specific way using multiple coatings of epoxies. Yeah. So those are things that you have to learn the skill set. Yeah. Good question. Yeah. But you can imagine the power of this technique. Okay, with the sensors always stay on your structure. When something happens, you know when and how it happened. That's the highest for forensic. Yeah. Yes.
But is this technique also useful after the crashes occur? Like, could you backtrace?
No. A damaged structure, you apply the strain gauge, it will be useless. Yeah.
In that case, you would only use the crack measurement machine.
Right. Yeah. You still have to go back to the old crack measurement. Yeah. True. Yeah. But on the other hand, if you wanted to, so sometimes you can stress test, like pressure tank leak problem. Sometimes we do what we call the stress testing. So you reapply the force and then use the crack opening to determine what was the condition before. This is called the Kaiser effect, okay? And you can use this kind of gauges because you don't care about the but you care about more the change in the crack during testing. Yeah. Very good question. Yeah, those are almost a little advanced than I expect. Yeah. Anyone else have questions? Some of you have never asked questions. You should.
What is the cost of this optical fiber?
Okay, very good question. So you probably are familiar with strain gauge. Okay, in the U.S., strain gauge each one is probably $5-6. A fiber optic sensor can be much cheaper. Why? Because one strain, you can put many strain gauges. Yeah. So that's why I got convinced with this technology. Yeah. In fact, the guy that developed this technology, I'm a very good friend. So every summer we go to his lab and then learn about this. Yeah. Because again, so fiber strain gauge work on 2 principles. One, again, it's all based on the reflected light from the, except this is guided wave, right? One is this strain gauge. So one wave goes through. If you have many strain gauge, which is impossible for actual strain gauge, the metallic strain gauge we use. For example, if you have a beam this long, if you put 1, 2, 3, 4, 5, 10 strain gauges, with all the wires, that's very expensive. But with this one line, and yeah, you can have so many strain gauges, hypothetically, yeah. So this is really a good technology. But then the challenge with this, the more you need, every strain gauge have to have its own limited band wavelength. So, then you limit it by how many your laser beam can travel. Yeah. And another thing that you notice that from this presentation is that I have not one technique but multiple techniques. Yeah. So this is the challenge for this profession is you almost have to have many tools in your pocket. So you see one problem, you can use this, maybe use another thing, maybe use another thing. Yeah.
Use the right technique.
Right technique. Yeah, for the right problem.
It's a multitude of the entire engineering in this.
Yeah. So this.
It's got lots to be.
Yeah. Yeah. But you know that's the. I think the reason why I go into this is really because I'm from a family of civil engineers. So my dad is also a civil engineer. My brother, sister, everybody's civil engineer. And but I'm more inclined during high school in medicine. You know, so in Singapore we choose our profession. So when I graduate high school, I don't really know what I want to do. I spent a year in Germany, wasting my time. Then my dad said, you have to go to college. So everybody is going to civil engineering, and they all go after what they interest. Like my sister loves chemistry, so she become an environmental engineer. My younger brother is very logical, so he go into transportation. So operations, research, and so forth. So I'm like, okay, since I don't have specific interest, I'll go into everything. And so, but really, what my strongest research interest really actually is in signal processing. Yeah, I like to look at. I spend a lot of time looking at waves and then see what the meaning of the waves, and I think that's why I went into geophysics and then do those signal processing. Yeah, that interests me more than anything else. Yeah. Any other questions? Yeah. Okay, then I think this is for today. Yeah. Thank you.
For lunch?
Yeah.
We
Yeah.
have an early lunch today.
Uh-huh,
Normally
yeah.
we used to go by 1.